Hello, good evening, my dear warriors, all the NEET 2024 aspirants who are ready to target 700 plus. I hope I'm audible as well as visible. Do let me know quickly in the chat box. Yep, very good, very good. Looks like I should be audible and visible. Good evening, Krishna. Hello, Baswa sir. Baswa sir is here. Yes, your Basvasaurus, sir. He's got a new name now. Hello, Partha. Hello, sweetie. Hello, everyone. Good evening. Hello, Irfan. Hello, sir. Good evening. Good evening. So it's time to start our next chapter, and that is heat transfer. Before this, I have completed kinetic theory of gases. I have completed thermodynamics. I have completed specific heat capacity of materials, gases, their relationships, as well as the concept of calorimetry. Even thermal expansion has been done. All these things have been done, and now it's time to complete the only part of thermal physics, which is heat transfer. We are also done with solids, elasticity. We're also done with fluid statics, fluid dynamics, Bernoulli's principle, all those things done. Surface tension also done, and even our viscosity is also done. So this is the only small part which is there, which will complete today, and you will definitely get one question. So 4 marks are guaranteed. So out of 700, slowly you keep on accumulating those marks. So that is what we are going to do today. With me, your physics Shreyas sir, Captain Shreyas. Yep, that's what you can call me as well. And today's session is going to be fascinating, just like every other session that we have. Hello, Rageshwari, waiting for my class. I'm so glad that you guys are back here. And now that board exams are over, the only thing that we are going to focus is, our NEET examination, right? That is what our main target should be. Uh, Sometimes it acts literally weirdly. Oh, yeah, I hope it is fine now. Okay, cool. So let's begin. And before I forget, let me tell you, I'm going to come to the following cities. This is my schedule right now in Pune, 21st March, 23rd March, we are going to come to Vizag, 24th in Hyderabad, and Tamil Nadu is going to come very soon. I'll announce the dates. What am I coming for? That is very important because many students need that final push, that final strategy, that final resources. So there are going to be workshops, there are going to be one-on-one interactions, guidance, and lot of things that you will learn in these particular workshops on these dates. So please come to these centers, Vedantu learning centers. In fact, there are many centers across India, and there are events happening many places. Check out the nearest center. In fact, there is a link which is there in the description box, and you will see the events and all the happenings which are being conducted at these centers. These centers are really amazing. I mean, these are not your normal offline centers, let me tell you that, because it's not just about the digital equipment and the facilities that you are going to get, but you once be there and you see the difference, the kind of personal attention, and you will feel so much at home. You will probably love these centers more than your home. That is the level of dedication which any teacher is putting over here. And I want you to feel at home. Use these spaces, use these libraries, use the facilities which are being provided to you. And there are no institutes which offer this Vedantu improvement promise, like guarantee, where if you don't improve the rank, then the money is refunded. Nobody will tell you these things, but only Vedantu is one of the institutes which does this. And we are so confident because we know that our students will do definitely very well, because material is good, teachers are good, facilities are there. There is nothing to stop. And there are neat crash courses for 5,000 rupees as well, which are being conducted at these centers. So if you want to, attend online crash course, that is also there, that option. And remember, the online crash course price is just for 1,999 rupees. Less than 2,000 rupees, you are getting the full syllabus with tests, assignments, everything, doubt solving, faculties, recordings, notes, everything. So you have both the options. You can visit the offline centers. You can study from home in case the center is not near you, right? Yep. Kinetic theory of gases is already done. Irfan, just check my old class. You will definitely be able to see KTG and thermo. Okay, so check my old class, right? Cool. Yes, I'll be definitely meeting you, sweetie, in Vizag and be there 23rd March, right, on Vizag, and 24th March in Hyderabad, Pune, 21st March. Tamil Nadu is coming soon. Okay, so let's begin with the lecture. Okay, so now starting off with heat transfer, like it says, what I'm doing now is knowledge transfer. I'm transferring the knowledge to you. Now, imagine I tell you I can transfer the knowledge via three different ways. Why three different ways? Like one way is, I put my hand over you and then I'm like, I'm blessing you. Hey, my dear kid, you know what? I bless you. You do very well in need, etc., etc. So, I touch your head and I give you blessings and suddenly you do really well. That is one way. That is like conduction, where you touch objects and you see the energy flows from one object to the other. That method is called conduction. Like you're holding a hot rod or a rod, and one side is kept in fire, like it is shown in this particular diagram right over here. Like it is shown in this particular diagram right over here, right? You can see that. So you can see one part is hot. The heat is going through the rod into the hands, and you will feel that burn. You will get repelled by that heat, and you're like, oh my God, let me just leave this rod away. That is why you see the pans which are used for frying chapatis, etc. They are coated with plastic or rubber or things like that because they are bad conductors of heat. So that is the first way of transferring heat. I told you knowledge transfer can happen by me giving you blessings and holding your head and saying, "Hey, I bless you." So heat transfer can also happen via touching. That is called as conduction. The second method is called as convection. Convection means, you know, the particles of the medium move from one place to the other and they carry the energy. In conduction, the particles don't move, they stay there. Like when you hold the rod on fire, the rod is not moving. The energy is flowing through the rod. Whereas in convection, the particles themselves move. That means this will not happen in solids, this will happen in liquids or in gases. Imagine one side of the room is very hot. After some time, that heat will come to the other side. Or if you turn on the AC on one side, after some time, the entire room will become cool. Correct? So, what is happening? The air molecules are moving from one side to the other. Even when you boil water, you are heating the bottom part of the water. The hot water floats because it is having less density, so it goes on the top, and the cold water comes down. There is circulation happening, and that cold water becomes hot, and it will replace that, and this warm water again gets heated up more, and again it replaces it. So there is circulation happening inside your body. What is happening? Circulation of what? Blood. What is blood doing? It is transferring heat to the entire body. That is how we are able to maintain the temperature. Come on, your bio students, you will definitely know this and appreciate this. Without blood, I don't think, the hand and the leg and the head, everything will be at the same temperature. Your blood is carrying that energy and maintaining that energy. So it is convection, flow of particles. Flow of particles. Very good. And the last one is basically radiation. Now, what is this radiation? Where the transfer of energy happens, but without any need of materials. Like, for example, the energy which comes from the sun. What is there between the sun and the earth? Is there water? Is there a rod? Is there air which is coming from the sun? We blowing air and it is coming over here. No, definitely not. So basically, radiation is where you don't need any medium. Medium is there, okay, fine. But that was not needed. It can transfer without anything. It goes in the form of electromagnetic waves. Electromagnetic waves. That is how it travels. So that is basically radiation. There is no need of medium. And it is the quickest way in which energy can flow from one side to the other side. So imagine somebody has lit some fire, wood somewhere, or bonfire. You feel the heat from far away. Have you experienced that? Especially in winters. And you have gone to hill station, maybe Ooty or Kodaikanal, right? or maybe you have gone to, I don't know, Coorg or something, nice hill station, Chikmagalur, right? And you're sitting over there and they light up bonfire and you feel the heat from a distance. What is that? It's not conduction. No rod is connected to your face. There is not much of convection. Even if the firewood is far away, obviously the air can't flow so easily to you. It is radiation, right? So some people are probably getting um, distracted also now. Sir, you're talking about Ooty and Kodaikanal and Chikmagalur and Coorg, sir. I miss these places, or I want to be to these places. Definitely, you should visit all these places after your NEET exam. After NEET exam, full on party, full on chill. Okay, till now, till then, what you should do? Study. So let's do conduction. Main questions in your NEET exam come from conduction. Uh, there is a good chance, 60% chance the question will be from conduction, 40% chance or even 35% chance the question will be from radiation. That is the usual trend what I have seen. Okay, so let's start with conduction first, and we will basically see the formulas related to conduction. Right. Good evening, Anita. And somebody was from Diksha Vedantu. Hello, Tarun Reddy. Nice to see you over here. From Karnataka, I'm guessing. From which city are you? Are you from Bangalore or some other place? Nice to see all of you. Hello, Kanakarao. Good evening. Um, yes, in winter morning, Amrita. Correct, correct. Radiation should we study? Yes, you should study radiation, but only few things. Whatever I teach you, just study that much because Newton's law of cooling and few things are deleted. So just study whatever I'm going to teach you. So let's study conduction first. Like I said, conduction is a mode of heat transfer which happens predominantly in solids, and the energy flows from one side to the other side without the medium having to move, without the medium having to move from one place to the other. Remember, this kind of heat transfer is mainly occurring in solids. This is mainly in solids. That is number one. Number two, this is a slow mode of transfer. It is a slow mode of transfer, not as fast as convection or radiation. Keep this in mind. These are few things which you should know. Uh, there are good conductors and bad conductors. So there are good conductors as well as bad conductors. So good conductors of heat are like metals usually. Metals are really good conductors of heat. Similarly, you have bad conductors of heat, bad conductors of heat, bad conductors of heat like wood, right? Then you can also talk about wool. Then you can also talk about plastic, rubber, all these things. In fact, you will see whatever are good conductors of electricity are also good conductors of heat. Bad conductors of electricity are also bad conductors of heat. Why? Can you think? Why can you think? Um, yes, yes, yes. Think. Yeah, yeah, Amrita, what is your question about convection? Convection is not there in your NEET syllabus. Just need to know what is convection. That's all. There is no formula in convection, no theory in convection. You should just know what is convection. That's all. Yeah. The reason for good conductors of electricity being good conductors of heat is because they have free electrons. And these electrons act like carriers of energy. They transfer their energy via collisions. So those free electrons are responsible. So that is the reason why you see that similarity in electricity as well as in heat transfer. Right? Got it? All right. Now, now there is an experiment which gives us the formula for the conduction which is happening in solids. So you take a solid object like a pipe or a rod or a column or a linear object like the one shown over here. You can see this particular thing is a rod, and I want to study how the heat is flowing in this rod. So what I do is one side of the rod I maintain some temperature, let's say Tc, and the other side of the rod, I maintain some temperature Td or Th or whatever you want to call. So some books, instead of Td, I can use the symbol Th. This Th, H stands for hot. So Th is definitely going to be more than Tc. Th is going to be more than Tc. H stands for hot. One side is hot, one side is cold. what does heat do? It will always go from hot side to the cold side. It will always go from the hot side to the cold side. So actually the mark over here, I need to change it, right? Okay, I will erase this maybe, I don't know. Okay, so actual direction, actual direction of heat should be from here to here. Heat always goes from the hot side to the cold side, something like this. Okay. Now, now, how much heat flows, how much heat flows per unit time can be calculated via experiments. Can be calculated, via experiments. And this experiment is conducted in laboratory. How much heat is flowing per unit time? And it is repeated for different dimensions of the rod, for different areas of the rod, for different materials of the rod. Once you make the rod of aluminum, then copper, then maybe cement, maybe marble, then stone, then plastic, then you change the temperatures, then you change the dimensions, you change the areas. So this experiment is repeated multiple times to get this particular law of conduction, to get this particular law of basically conduction. And what is being found is the following. One second. Okay. Yeah. What is being observed is the following. The rate of heat flow, the rate of heat flow, which is also called as the heat current. Heat current. How many joules is flowing per unit time is found out to be proportional to, is found out to be proportional to, the following things. The area, right? It is being found out to be, just one second, let me get some water. Yes. Okay. Yeah. It is found out to be proportional to number one, the area of the cross section. That is number one thing. The second thing, it is found out to be proportional to the difference of the temperature between the ends of the rod. That means the hot temperature minus the cold temperature. And it is also found out to be inversely proportional. It is also found out to be inversely proportional to the length of the rod. Inversely proportional to the length of the rod. Hello GP King, welcome from Tamil Nadu. So these are the three things which it was found out to be proportional or inversely proportional to. Now you might be asking, sir, what is the symbol for heat current? Well, the symbol for heat current, the symbol for heat current is nothing but dq by dt. Heat flowing per unit time, dq by dt. Makes sense. Joules per second. Q is heat. Q is the symbol of heat. And dt is nothing but the time taken. So dq by dt is the rate of heat flow. It's nothing but the rate of heat flow, which is also heat current. It is expressed in joules per second. So I'll put the units also over here. I'll also put the units over here. Joules per second. Or you can also use the unit of watt. Or you can also use the unit of watts. Joules per second is also watt. Perfect. So combining all these things together, what do I get? Our heat current, which is dq by dt, our heat current, which is dq by dt, will be nothing but equal to, I don't want proportionality, I want equality, is equal to some constant, I'll put it as k, some constant, I'll put it as k, into area, into the temperature difference, which means Th minus Tc, the whole thing divided by length, whole thing divided by the length. This is the formula that one gets after writing it in the form of equality. After writing it in the form of equality. So what is this constant K, you might ask? This constant K is basically called as the conductivity of the material. conductivity. What is this called? This is called as conductivity of the material. Conductivity of the material. It depends on the material. So, if you talk about a good conductor, if you talk about a good conductor like metals, the value of K for such materials is very high. The conductivity is high. If you talk about bad conductors, their conductivity K value is going to be very low. Yes, it depends only on the material. The K value decides it. Good conductor or bad conductor is decided by the value of K. Now, just one second, guys. This, yeah. Now, every time it is not necessary you will have to use this formula. Sometimes the formula might change little bit because you are not applying for a long rod but a section of the rod. Imagine out of this big rod that you have, you take a section out of it. Imagine a section is like this. Imagine the section is like this, whose width whose width is example dx, whose width is basically dx. And imagine the area of that section is A. And imagine you take such a section. So I will show it over here. Let's say like this. It looks maybe like this. This is your dx. This has some area A. And through this section, your heat is flowing. Through this section, imagine your heat is flowing like this. Your heat is flowing like this, right? So there is dq by dt. In such a case, the formula will slightly look similar, but actual values will change little bit. It will look like this. dq by dt, right? dq by dt will be, k will be there as it is. K will be there as it is. Even area will be there as it is. Even area will be there as it is. But instead of temperature difference, and that length term, what will you have? What will you have? Think about it. You will have the small temperature difference dt upon the small length, which is basically dx. What is dt? It is basically the temperature difference across the cross section. It is the small temperature difference. Small temperature difference. Small temperature difference. This is very, very important. Yeah, very good. I'm very good, Rupesh. Thank you. Yeah, very good. Sometimes this term which is there, dt by dx, this term which is there, dt by dx, is also referred to as a combined quantity as the temperature gradient. You might hear this word often. Temperature gradient. What is it called? Temperature gradient. Imagine a question like this on it. Imagine a question like this on it. Say, they tell you, listen, there is a rod, there is a rod with with a temperature, with a gradient, temperature gradient of, oh, by the way, what will be the unit of temperature gradient? Can you think? Temperature per unit length. So the unit of temperature gradient will be Kelvin per meter, Kelvin per meter, or you can also use degrees centigrade per centimeter, etc. All those units are fine. Its meter is there in the inverse and temperature is there in the numerator. Perfect. So imagine a rod with a temperature gradient of, let's say, 10 Kelvin per meter and heat flow intensity, heat flow intensity of 20 20 watts per meter square. Find, question is find the conductivity. Find the conductivity. You might be wondering, sir, this problem looks to me like a little bit, out of the box. But let me tell you, it is not really. See, let's understand what and all is given. And how can I relate it to the formula? Our formula, our formula is as follows. Let me just put myself here. Our formula is as follows. dq by dt, dq by dt is nothing but k a dt by dx. Why am I using this? Because I see this word temperature gradient. Moment I see this word temperature gradient, it should click in our mind that I should use dt by dx formula. Now, okay, dt by dx is given to me. dt by dx is given to me 10 Kelvin per meter. But dq by dt is not given to me. Look at the units. What is given? 20 watts per meter square. Oh, what is actually given? You should think or take the clue, hint from the units. Watts is the unit of dq by dt. Meter square is the unit of area. So actually what is given is your dq by dt, if you divide it by area, is equal to k into dt by dx. This LHS is the heat current per unit area. Heat current per unit area. So the heat current per unit area, which is that heat flow intensity, they have used some fancy word. Doesn't matter. Don't get scared by it. So actually what is given is dq by dt by area is 20. K value is not given. dt by dx is temperature gradient, which is this particular value of 10. So I'll put it over here. So K value will be 2. Understood, my dear students, how this has to be done? Okay. So sometimes they might twist the question a little bit here and there and give it to you. So always take hint from the problem. Something will be there which will give you the clue. Now, there is a very interesting analogy of heat transfer, especially conduction, when you compare it with, your current electricity. And I will tell you how. Hello, Demon Gaming. Understood, Cap2. Very good, Krishna. Hello. Welcome all the students who are joining in little bit late. Start watching the class from here. Whatever part you missed, you can watch it later. Imagine you take a rod like this. Okay. Imagine you take a rod like this. Okay. And it has some length, it has some area, it has some thermal conductivity. Okay. And then we write the formula as follows: dq by dt, dq by dt is nothing but k a delta t by that complete length, by that complete length. Okay. So I'll rearrange the formula a little bit. Okay. So imagine if I write delta t is equal to dq by dt, dq by dt as it is. So I'm taking length on the top, k and a below over here. So you will see length will go on the top and divided by k a. I'll just leave it as it is over here. Okay, I'll just leave it as it is over here. I'm not going to do anything right now. Now compare this with your current electricity resistance. Current electricity resistance. This was resistance. This is current flowing through it. And there is some voltage difference across the two terminals of that resistor. According to Ohm's law, according to Ohm's law, isn't the voltage difference equal to the current flowing through it multiplied by the resistance? Yep, correct. Now, compare this equation with this equation. You will understand what I am hinting at. Look at what delta T actually is. Delta T actually tells you the temperature difference. Temperature difference. In current electricity, it tells you the voltage difference. Here, this dq by dt is the rate of heat flow, which is called as heat current, which is called as heat current. In current electricity, it is just called as current. So, just like voltage difference is current multiplied by resistance, same way temperature difference will be heat current multiplied by what resistance? Yup, this will be resistance, but in thermal physics. That's why it is called as thermal resistance. That's why it is also called as thermal resistance. Which means whenever you are given a rod you can convert it into a current electricity problem. You can use Kirchhoff's current law, Kirchhoff's voltage law. All these laws are even applicable for conduction. You can treat the rods, as resistors, where our thermal resistance, where our thermal resistance RTH stands for the thermal resistance is nothing but L by Ka. L by Ka. This is a very fascinating thing with regards to current electricity and heat transfer, how they are related, how two different chapters of two different units of two different standards are actually related to each other. It's amazing. I'm very good, Akila Devi. Good evening. Hello, Akash. Hello, Anasul. Nice to see all of you. What a brilliant, brilliant correlation. So, imagine rods in series and parallel. This becomes so easy. Look at this, my dear students, now. Okay, let me just create a duplicate for this. Just imagine I will give you two rods like this. They could be of different lengths, different conductivity, etc. Imagine this is L1, this is L2, this is K1, this is K2. Okay, area is A. Can I combine it together into one single rod of area A, conductivity K, and total length L1 plus N2? Definitely I can. Because I know both these rods are one after the other, and I know that the same heat flow will pass through it. The same, the same heat will pass through both the rods, just like one resistor after the other. So dq by dt is same. dq by dt is same. Heat current is same. Just like resistors in series, what is same? Current flowing through them is same. Exactly. So I can just say R1 resistance plus R2 resistance is equal to the equivalent resistance in series. Equivalent resistance in series. That's all. What is the formula for thermal resistance? I just gave you. It is L by K. It is nothing but L by K. So all I'm going to do is write L by K into A plus L by K into A is equal to L now will be for the total rod, which is L1 plus L2, L1 plus L2, and divided by the equivalent K into basically A. You will see AA will get cancelled, and you can get 1 by Ks is equal to here you will have L1 by K1 plus L2 by K2, and what I have done is this L1 plus L2 I bring it down over here. I'll bring it down over here. So 1 by L1 plus L2. From this, I will get the value of Ks. Do you need to by heart it? No. But do you need to know the procedure? Yes. That's all I'm asking you to remember. Is that okay? So this is how you can find equivalent thermal conductivity of two rods connected in series. Use resistors in series formula. Okay. What about resistors in parallel or rods in parallel? How will they look like? Imagine one rod over here like this and another rod beside it like this, maybe over here. This is having some area 1, this is having some area 2. Both of them are having the same length. This is material 1, this is material 2. I will combine them into one single rod of area A1 plus A2 and the same length. There will be some heat flowing through this rod. There will be some heat flowing through this rod. Through this particular rod, which is the equivalent rod, I will say, I will say that the heat currents are not same. But if through this rod, the heat current was dq1 by dt and the current through this rod is dq2 by dt, then the total heat current will be through the equivalent rod dq1 plus or dq1 by dt plus dq2 by dt. The heat currents will add. What will I say? Heat currents. The heat currents will not be the same. Heat currents will add up. That is the most important thing over here. Exactly. Yes. Everyone with me on this? So, just like resistors in parallel, what happens? 1 by R1 plus 1 by R2 is nothing but 1 by R. Same way, 1 by R1 plus 1 by R2 will be nothing but 1 by R in parallel. Remember, our thermal resistance was nothing but L by Ka. So use that over here. So L by K is the resistance. So 1 by R1 will be L by K over here and A over here. K is different, area is different. Plus K2 A2 divided by length. Remember the length is going to be the same, is equal to K equivalent. I will just call it as Kp. Area will be A1 plus A2, the whole thing divided by length. Length will cancel from everywhere. So when I find the value of Kp, I will have K1 A1 plus K2 A2, the whole thing divided by, because A1 plus A2, I'll bring it down over here. So A1 plus A2 over here. That's how I can find the equivalent thermal conductivity. That's how I can find out the equivalent thermal conductivity. Is that very, very clear? Yes, awesome. So keep all these things in mind. Keep all these things in mind. Very, very important. Right. Now, I think we can solve some questions based out of it. Right. So we have done the concept of thermal resistance. We have done the concept of series parallel. We have done a basic question on this, and what is the formula and what is the meaning of conductivity, right? So this is the main theory. There are many variations in the problem now. So let's do those variations. Okay. The coefficient of thermal conductivity depends on what? The temperature difference, area of the plate, thickness of the plate, material of the plate. I want everybody to spam the answer right now. I want everybody to spam the answer right away, right now. Come on. Yes, thermal conductivity is a materialistic property. It will not depend on the temperature difference. It will not depend on the area of the plate. It will not depend on the thickness of the plate. Exactly. It will just depend on the material of the plate. Exactly. So the answer is material. Very good. Keep it up. So good conductors have more K. Bad conductors have a very low value of K. D for doctor. Yes. D for doctor is the answer. What is the dimension of thermal resistance? This you'll have to work out a little bit. This was, by the way, asked in Neet exam many times. So, you can take it as an important question, and these kind of questions do come. And you can do this only if you know the formula. You cannot sit and by heart this thing. So what you will do is, dq by dt is Ka dt by dx. So dq by dt is nothing but joules per second. So I will just put it as the dimension of energy, which is m1 L square, T raised to minus 2 divided by times dimension is T raised to 1 is equal to dimension of thermal conductivity. I don't know. That is what I need to find. Area's dimension is L square and dt temperature is Kelvin. So put K, and length is basically L over here. Just rearrange and see what is the dimension of conductivity is what you are getting. What is the dimension of conductivity that you are getting? Come on, my dear students. See what you are getting. I think m will be raised to 1 because nowhere else m's power is there. Nowhere else m's power is there. Come on, my dear warriors, what will it be? Think about it. M's power is only there once over there, right? So m raised to 1 will be there. What else? Yep. What is the power of L? Do you see? Do you see L square and L square just got cancelled over here? Do you see L square and L square just got cancelled over here, right? Perfect. Then times power will become minus 3, t raised to minus 3 over here. Very good, because t raised to minus 2 is there, t raised to 1 is there. So when t raised to 1 goes on the top, it will become t raised to minus 1. So it will become t raised to minus 3. And this length will come on the top now. This particular length will come on the top over here. So it will become L raised to 1. So M1 T raised to minus 3 and length raised to 1. And lastly, this Kelvin will go below. This Kelvin will go below. That's all. This will go below. So that is the dimensions of thermal conductivity. But in the question, they have asked thermal resistance. My bad. I was trying to find conductivity. I don't know why I went to thermal conductivity. My bad. This was for thermal conductivity, my dear warriors, but none of the options will also match. We had to find for thermal resistance, not conductivity. So if we want to find for thermal resistance, or thermal resistance. Thermal resistance is nothing but L by Ka is what you can use, or resistance, just like V is equal to IR. R will be voltage by current. It will be temperature difference by the heat current, which means it will be dq by dt. dq by dt. I think this is a much better formula to use rather than this one. So temperature difference is basically in Kelvin. Temperature difference is basically in Kelvin. dq by dt. dq is energy. Energy is nothing but m1 L raised to 2 T raised to minus 2 by dt. By dt means basically time. That means seconds. So time will come over here. Take it on the top. So it will become K into T, and then you have m raised to 1 L square T raised to minus 2. Solve this and see what you get. You will basically get m raised to minus 1. You will get L raised to minus 2. You will also get T raised to plus 3. And you will also get a Kelvin over here, which I believe is option number A. Which I believe is option number A. And it should be option A. Yes, it is option. Got it? How we did this? So I have done both the problems. One I have done it for conductivity, because this can be also a question. You can also do the problem for thermal resistance. So both varieties of question I have done. Yeah. Number A for A. Correct. Very good. Now look at this. This is there in your NCERT exercise 10.6. There is some furnace. Okay. And copper steel junction is there. Steady state length. Rod length is given. Copper rod length is given. Temperature of the furnace is given, other end temperature is given, area of cross section of the steel is twice that of the copper is given, thermal conductivity is given of copper and steel. What is the question? What is the question is what is the temperature of the steel copper junction? This is the question. That means at this point they are asking you what is the temperature. What is the temperature? That is what the question says. Now there are many ways of solving this question. But I feel the easiest way is by remembering a fact that whenever resistors are in series, current is the same. So when rods are in series, what is same? Current is the same. Many people think, so the rods are in series, so I need to, go back and think of how do I make it into an equivalent rod in series like the one I have done over here. Should I do that? I don't think there is any need for that. There is no need for that because they have not asked you what is the equivalent thermal coefficient, what is the equivalent thermal resistance. No, they have not asked you anything like that. They're just asking you temperature. So for these kind of questions, right, all you need to do is remember the fact that the heat current will remain the same. What will remain the same? The heat current. Keep this in mind. So it's the heat current. So it's the heat current. It's the heat current remains the same. Heat current remains basically the same. Is that clear? Everyone with me on this? Very good. Now, when I say heat current is the same, can I say that dq by dt? Why did I say this, by the way? This is because only they are in series. Dq by dt in the steel rod will be also dq by dt in the copper rod. In the copper rod. Very good. So what is the formula for dq by dt? Ka dt by dx, or Ka temperature difference by the length. K of steel. What is it? It is basically 50.2 multiplied by area of cross section. Is it given? Oh, it is just given that the area of cross section of the steel is twice. So I'll put it as 2a. Temperature difference in steel, one side is 300, other side is x. One side is 300, other side is x. So 300 minus x will come. The whole thing divided by the length of the steel rod. Length of the steel rod is 15 centimeters, or I can also put it as 15 into 10 to the power minus 2. That is what this is. That is what this is. Is that right? That is dq by dt for steel. Do the same thing for copper. Do the same thing for copper. What is the copper's conductivity? It is 385 SI units. Area of cross section of copper, I will assume it as A. Temperature difference between the copper will be x minus 0, always higher minus lower. So x minus 0. The whole thing divided by length of the copper. Length of the copper is basically 10 centimeters. It's given over here. So 10 into 10 to the power minus 2. Yes, Supriya, you can watch it definitely. Yes. Now do you see everything is known except for x in this equation? Start doing the cancellation, start doing those calculations. You will get the value of x. That part I leave it up to you, right? So solving it, you will get the answer as 44.4 degrees. 44.4 degrees. Is that clear how to solve it? You will be able to solve it after this because you will see many things will get cancelled. Like area over here, area over here, 10 to the power minus 2 over here, 10 to the power minus 2 over here, right? All these things. This 10 is divisible 5, it will become 2. 15 is divisible by 5, it will become 3, right? After this, you just rearrange it and you will get the value of x. That is not that. Okay, great. So these kind of questions always equate the heat current. Don't find the equivalent conductivity. It is of no use. Moving ahead. Okay. See this. This kind of question, this kind of question is again repeated in NCERT, right? I will come back to this question after the PYQs. I'll tell you why also. You will see same kind of questions which is there in NCERT. You see the question. Temperature at the junction is asked. Equivalent conductivity is asked. Heat current is asked. Same kind of questions have come in NEET exam. That's why NCERT is so important. That's why NCERT is so important. Sebastian, concentrate on the class, not on anything else. Concentrate on the class. So look at this. Two rods, one made of copper, other made of steel, same length, same cross section, joined together. Conductivity of copper and conductivity of steel is given. Free ends of copper are at 100 and 0. The temperature at the junction is approximately. It's just like your previous NCERT problem. See if this makes sense to you. It's just like your NCERT problem now, right? So steel and copper both are of same length, same area. That's all. Length is also same, area is also same. One is copper, one is steel. What will be same? Heat current will be same. So dq by dt here in copper will be dq by dt in basically steel. What is dq by dt in copper? Well, it is nothing but k of copper is nothing but 385 into area, which is A. Temperature difference, well, it is given to you that copper is maintained at 100 and steel is at 0. So this side is at 100 degrees Celsius. This side is at 0 degrees Celsius. This is at X degrees Celsius, which I do not know how much it is. So the temperature difference technically will be 100 minus X over here. That's it. And the whole thing divided by the length. Whole thing divided by the length. And over here, thermal conductivity of steel, it is 50. Area is nothing but A multiplied by the temperature difference. Can you see? It is nothing but X minus 0. It is nothing but X minus 0. The whole thing divided by the length. Now length, area will cancel. Length, area will cancel. So you will just be left with 385 into 100 minus x is equal to 50x. That's all. Now solve this for x and you will get the answer. Solve this for x and you will get the answer. What is the answer you will get? Just check it if you get it as 88.5 degrees Celsius. Yes, just solve this equation. Just expand this, nothing more to do. So just do 385 multiplied by 100 minus 385x is equal to 50x. So basically 385 multiplied by 100 is equal to, take x common and put 50 plus 385. So solve this and you should get it close to 88.5 degree centigrade. Got it? Hello Moni, thank you for all the love from Tamil Nadu. Glad to see all the new students, and I feel really happy when you comment with your name and your state or your place, and I get to know more about you. And make sure that you're regular and keep spamming the answers, keep interacting, and keep making friends, because it's the last 1.5 months of your entire NEET journey. Yes, after this, it will be time to say bye bye to all of you, because you will be entering the government medical college, AIMS, AFMC, JIPMER, God knows. So, last 1.5 months on this channel for all of you. Cool. So this is done. Moving on to the next question. Like you say, that these questions are completely based out of NCRT. Completely based out of NCRT. That is the reason why I'm doing it over here. These are all PYQs. This was asked in NEET 2022, which I just did. This kind of question has also come again. So there are two wires of identical lengths having some circular cross section. Radius of A is double the radius of B. And it is also mentioned that the temperature difference between the two ends of both the wires of the conduction heats at the same rate. Okay, the relationship between the thermal conductivity is given. So area of cross section will be different because the radius is different. For that given temperature difference, both wires conduct heat at the same rate. Very, very important. They conduct heat at the same rate is what is given to you. That means dq by dt, heat current in the first rod, is a dq by dt in the second rod, as per the given information. Information. Correct. Yes, RCB, the women team won for the first time. Like they say, ladies first. So RCB team took it very, very seriously, looks like. Correct. So dq by dt will be nothing but k of the first rod into area of the first rod, delta t by length is the same, and K2, A2, temperature difference is the same, divided by the length. Very nice. Delta T cancels. Length also cancels. So K into area is nothing but pi R1 square is equal to K2 into pi R2 square. Even pi cancels. Now clearly the first radius is double the second radius. So I can just say R1 is 2 times of R2 whole square, and this will be K2 into R2 square. So therefore, I will have 4 times of K1, because R2 square will cancel out. 4 times of K1 will be equal to K2. 4K1 is equal to K2. That is option number D. Here 1 is A, B is 2. That's one. Yeah. D for doctor. Yes, Krishna. Yes, Siva Prasad. And nice to see that logo on you, Siva Prasad. That means you have been regular on this channel for a very, very long time. I'm really, really happy. Keep it up, keep it up, keep it up. Let me tell you, this chapter is so important that you will 100% get one question on this. 4 marks are guaranteed. Okay, moving on. Cylindrical rod has some temperature T1, T2 at the end. Rate of flow of heat is Q1. If all the dimensions are doubled while keeping the temperature constant, then the rate of flow of heat will be how much? Rate of flow of heat will be how much? Observe the question. This is AIPMT question, which can be again asked in NEET examination, definitely. So what we need to do over here? Okay. So the rate of flow of heat is this much. If all the linear dimensions are doubled, that means length has been doubled, radius has been doubled. Keeping the temperature difference constant, what will happen to the new heat flow rate? dq by dt, dq by dt is K A dt, or basically temperature difference by the length. I don't like area term because radius has been doubled. Let me write in terms of radius. K pi r square delta t divided by length. So can I say dq by dt technically is proportional to r square and inversely proportional to length? Now, as per the given information, since the radius is doubled, so the numerator is made 4 times. Numerator is made 4 times because 2 square is basically 4. and the denominator is increased two times. So numerator is increased 4 times, denominator is increased 4 times. So what will be the ratio going to change by? What is the ratio going to change by? It is going to change 2 times. So into 2. Yes, the answer will be B for biology. B for biology. Perfect. So the correct answer is it will become double. So always find the relationship. If you know the formula, you see what is given, what is constant. K was constant, pi constant, temperature difference same because temperatures were given. So only the lengths were changed like radius and length. So you find the relationship, how it is proportional, inversely proportional, and you will get the answer, right? Moving ahead to another question coming up on your screen. Consider a compound slab consisting of two different materials of having equal thickness and thermal conductivity given by K and 2K. Thickness is same, that means area of cross section is same. Conductivity is different, K and 2K. The equivalent conductivity of the slab will be how much? Okay, thickness is same, area is same. So just think of it like this. This is K, this is 2K, this is L. If this is A, this is also A. When rods are in series, just add their thermal resistance. And here we need to use equivalent resistance formula because the question is on finding the equivalent conductivity. So I will just say R1 plus R2 is the equivalent resistance in series. R is nothing but L by K. L is L for the first rod. K is nothing but K. Area is A. Second rod, length is L. Thermal conductivity is 2K. Area is nothing but A. Resistor in series, equivalent is asked. So when you combine both the rods as one single rod, the total length of the rod, how much will it be? It will be nothing but 2L. It will be nothing but 2L, right? That is one common mistake which students do. They forget this number 2, you will lose marks. 2L divided by K equivalent, whatever that equivalent K is, and the same area. Many things are going to get cancelled right over here. Length, length, length. Area, area, area. What am I left with? 1 by K plus 1 by 2K. 1 by K plus 1 by 2K is equal to 2 by K equivalent. Taking LCM, LCM is 2K, and here I will write 2 plus 1. 2 plus 1 is equal to 2 by K equivalent. 2 plus 1 is 3. So 3 by 2K, and that 2 will come on here. So 2 into 2K is equal to 1 by K equivalent. So basically my K equivalent will be 2 2s are 4. So 4K and 3 comes below. 4K by 3. 4K by 3. Where is it? D for Ames Delhi. D for Delhi. Ames Delhi. That is the answer. Yes. Is that clear, my dear students? Is that clear, my dear students? Very good. Is it parallel? No. If you see they have equal thickness, they're equivalent. Consider a compound slab. When I say compound slab, okay, generally consider it like this, not besides each other. I know that confusion can be there. So it is always better to have a diagram, but compound slab means one after the other, and the heat flows from one slab to the next slab. So it is flowing from one after the next. So they are one after the other means they will be in series. Okay, I hope this is clear. Very good. Very good. Moving ahead, moving ahead. This was the NCRT question which I wanted to show you that, you will see that all the questions, whatever we did in previous years, is actually picked up from NCRT with values changed. Check this out. First question. The temperature of the junction of the two bars. Isn't it this particular question? Just check this out. This was asked in Neet 2022. Check this out. Question is, what is the temperature of the junction? Check this. What is the temperature of the junction? Exact same question, but values have been changed. Then check another question which is asked over here. Equivalent thermal conductivity of the compound bar. Equivalent thermal conductivity. This is asked in AIPMT if you notice. Equivalent thermal conductivity of the compound slab. Of the compound slab. Yes. So all these things are basically directly picked up from NCRT, my dear students. Heat current is probably not, or maybe I'm not just picked up the question right now, but If it is not yet asked, maybe this time you will get heat current through the bar. If this question comes, what is the heat current flowing through the bar? What will you do? If the question is finding the heat current through the bar, what will you do, my dear students? Think about it. Heat current through the bar, right? If such a question comes, what will you do? You will say dq by dt, dq by dt is the total K. What is the total K? K equivalent into area, okay, into delta T divided by the total length. Total length, L effective, right? K equivalent is basically 4K by 3. Area is A, delta T is delta T only, and the length effective is basically 2L. So basically you will see that this 2 will cancel with this 4 and you will be just left with a 2 over here. So that is the dq by dt, the heat current flowing through it. Awesome. So basically what you are seeing is that these questions are very straightforward, and whatever NCERT questions are there can get repeated in PYQs. And if you see some NCERT question is not yet repeated, so be alert, maybe that question might come. Who knows? Okay. So this is what I wanted to show you. Next, a metallic rod in thermal contact with two reservoirs of heat at its two ends conducts an amount of heat Q in time t. The rod is melted and the material is formed into a rod of half the radius of the original rod. What is the amount of heat conducted by the new rod when placed in thermal contact with the reservoirs in time? Alright, let's see what this question means. See, two reservoirs are given. That means one side has one temperature, other side has other temperature. Reservoir means something which maintains. So maintains what? Temperature. So if I have two reservoirs, one is hot, one is cold, so they are going to maintain a temperature difference. So delta T is going to be the same. Number one. Heat amount which is flowing is Q in time T, so I know the heat current. It is melted and formed into a rod of half the radius of the original rod. Now, this is the key part of the statement. The metallic rod is melted into half the radius of the original rod, meaning the volume will remain the same. Volume, volume is basically a constant. Volume is basically a constant. Okay, great. So what is the volume of a rod? It is nothing but pi r square into the length. If this is the original volume, the final volume will be pi r1 square into that new length. I can call it, instead of r1, r2 into L2. This is what it is. But I know the final radius, is half the original radius. So I'll just put it as r by 2 whole square. R by 2 whole square. So pi cancels, r square cancels. So L will be equal to 1 by 4 into L2, or rather L2 will be 4 times of the original length. So I now know the lengths are different. I know the radius is different. So obviously you will see the heat flow rate might also change. And what is the heat flow rate given? Heat flow rate dq by dt, is K A delta T divided by the length. Area I don't like. I will write it as pi into r square, and length will come here. That means it is proportional to r square and inversely proportional to length. I think this kind of question was repeated previously. This kind of question was repeated previously. Do you remember where? See this over here. This was asked in AIPMT 2001. 2001. Radius is changing, length is changing, but they have asked it little differently over here. And now if you notice, in this question, they have just kept the volume constant, but at the end of the day, you are getting the same kind of relationship. So what is happening at the top is that the radius has become half. Radius has become half. So this will become half square times. The length has become how many times? 4 times. Has become 4 times. So numerator changes by half, denominator changes by 4. So half square, sorry. Half square is basically 1 by 4. Half square is basically 1 by 4. So numerator has become 1/4. Denominator is 4 times. So as a whole, it will be 1 by 4 into 1 by 4, which will make it 1 by 16th of the time. So hence the answer will be Q by 16. Hence the answer will be Q by 16. Got it? Do you see how an old question from AIPMT or even a JIPMER question can also come in the NEET examination? So don't ignore very old questions. That is what my humble request is. Right. Then there is one type of typical question which can come on ice formation over lakes, and many people tend to skip this particular question or pattern of question. Let me explain this to you. See, if you talk about density of water, there is a very peculiar graph of it, and this graph leads to the ice formation of lakes. What happens is, if you look at the density of water versus temperature, that graph looks something like this. That graph looks something like this, my dear warriors. Okay. Do you see it is going down and then it again goes up? It is going down and then again it basically goes up. Yes, you will see that. And you will see that the least value, oops, wait, I did it reverse. My bad. I have to do it opposite. Yeah, not like this, my bad. Yeah. So the highest value of the density comes out at 4 degrees Celsius. Max density. Max density happens at 4 degrees Celsius. This behavior of ice between 0 to 4 degrees Celsius, where when you heat it, instead of expanding and reducing the density, it increases the density. So that behavior is called as anomalous behavior. This is called as anomalous behavior of water. This happens with water between 0 to 4 degrees centigrade. Is that clear? Guys, please don't spam and waste your time over here like this. I'll be putting you guys on timeout if you are doing unnecessary things. There is no female student. No, there are. Some people are shy to chat. That's all. Yeah. Yeah. So please don't spam or else I'll have to put you guys on timeout. Yeah. Spam regarding the content, spam regarding the explanation, the theory and all those things or the answers. Don't waste your time with unnecessary nonsense, right? Okay. So because of this, what happens is, imagine you have water over a lake. This is the lake bed. Lake bed. The outside atmosphere is very, very cold. Imagine the outside atmosphere is very, very cold. The water over here is warm. So what will happen? The heat will always go from the hot side to the cold side. So this is the direction in which the heat will flow. The first layer which will become cold is the topmost layer. So this will be cooler. This will be cooler. And the relatively warmer layer will be below. Relatively warmer layer will be below. Is that right? Everybody with me? Everybody with me? Right? Very good. Very good. So just imagine this. Yeah, just imagine this now. The outside temperature is cold. The water on the top is becoming cool. So the colder water is usually more dense. Just look at this part of the graph till 4 degrees Celsius. If you just look at this part of the graph till 4 degrees Celsius, my dear warriors, don't look at anything else. Don't look at anything else. Just till 4 degrees Celsius, you look at the graph. The water's density should increase, right, as you lower the temperature. That means the colder water, what will happen? The colder water will fall down. And as the water heats up, what should happen? It should rise up. It should rise up. This is how the convection currents will happen. This is how the convection of the currents will happen usually. But imagine the water's temperature drops below 4 degrees Celsius. So this circulation is till or above 4 degree centigrade. Now just imagine the outside temperature is very cold. This is very cold right now. And here you have the cold surface of the water. This is the bed of the lake. That means the bottom of the lake. This is the lake bed over here. If the water's temperature drops below 4 degrees Celsius, what will happen? If the temperature falls down, it will become less dense. It will become less dense. So this cooler water, this cooler water, what will happen? It will not go below. It will stay on the top, and the warmer water will will also stay below only, because the warmer water means the water which is at 4 degrees Celsius. The water which is at basically 4 degrees Celsius is more dense, highest density. The water which is cold, which is less than 4 degrees centigrade, is basically rare. It is less dense. It is basically less dense. The one which is at 4 degrees Celsius is more dense. So it will keep on floating. It will no longer circulate, and eventually it will freeze. Eventually, what will happen? It will basically freeze. So from this situation, it came to this situation, and finally, you will have finally what you will have is a layer of ice which is getting formed over here. You will have a layer of ice which is getting formed over here, because the topmost layer, is the coldest one, and slowly it becomes cooler, and finally it becomes ice. So you will have the trapped water which is 4 degrees Celsius, ice which is there over here, and very cold atmosphere outside. Very cold atmosphere outside. Finally, did you guys understand this? Finally, did you guys understand this? How this, ice formation happens on the lake purely because of anomalous behavior of water. Till the time the temperature is above 4 degrees Celsius, the colder water is more dense, it will come below, and the warmer water will rise up. This circulation keeps happening. But once the temperature becomes less than 4 degrees Celsius outside, then the colder water, will not increase density, it will reduce density, it will become lighter. So it will float, and it keeps floating, and the temperature reduces till it becomes zero, and the water will freeze, and that layer gets formed, and the warm water stays below. And that's why you will see the fishes are safe even in cold countries, even when the temperature drops below 0 degrees Celsius. So you will probably see fishes going over here. Let me show a beautiful fish. Yeah, marine life can thrive. Marine life can thrive only because of this particular anomalous behavior of water. Now, there is a formula for ice formation over lakes, and there is a very simple derivation for it. Imagine you have a layer of ice, okay, and let's say the thickness of the ice layer, let's say the thickness of the ice layer is basically y, and the outside temperature is, let's say, minus T degrees centigrade, minus T degrees centigrade. Inside temperature is 4 degrees centigrade, which is below the ice layer. Remember, this is that ice layer. And this ice layer is spread on that lake like this. Okay, this is a big lake like that. So it has some area of cross section like this, area of cross section like this. Remember why I have put minus T? Because imagine minus 30 degrees centigrade, minus 40 degrees centigrade. So T is basically the 30 or 40 like that. The heat will flow via the ice from hot to the cold side. So the heat flow will be like this. So this will be your dq by dt. Because the heat is being taken from the below part to the top part. So when you take away heat from water, what will happen? It will freeze. You will see an extra layer of ice getting formed as the heat gets taken out. So you will probably see there will be an small extra layer, there will be a small extra layer like this. This is that extra layer. I hope you are able to visualize this. This is that extra layer, and I will call that thickness as dy, that extra layer of ice which is formed. Why is it formed? Due to the heat flow. Due to the heat flow. Keep this in mind. Yes, perfect. Now, I know that whenever you take away some heat from water and that water freezes into ice, the water freezes into ice, there is latent heat of, solidification, fusion, which is involved. So, when you form that extra layer of ice due to the heat flow, can I not say the heat which is being taken out from the water to freeze it is nothing but that mass which is being formed of ice into the latent heat. Why dm? Because it's a thin layer of thickness dy, so the mass will also be dm. The mass will also be dm, and that mass can be written down as density into the volume of that layer. Imagine that sheet, it has a thin layer, and what will be the volume? The volume will be area of cross section into dy. Area of cross section into dy. Is this point clear to this, everyone? Yes. What is this L? If you are wondering, this is your latent heat for freezing. Latent heat for freezing of ice or solidification, fusion, etc. And this dm, what have I done? This mass is nothing but density into volume. Density multiplied by the volume. And this volume, I've just written it down as area multiplied by the thickness delta y. Area multiplied by the thickness delta y. Now what I get is an idea that how about dividing this dq with the dt. So this will be rho a dy by dt into latent heat. And I know what dq by dt stands for. Rate of heat flow. Rate of heat flow is k. A is the area. Temperature difference. Temperature difference will be, check this out, 4 minus T. 4 minus T, hot minus cold, divided by the length. Now the length of it will be the thickness of that ice through which the heat flows. So it will be nothing but just Y is equal to rho A dy by dt into L. Rho A dy by dt into L. You will see area gets cancelled from both the sides. Area gets cancelled from both the sides, and I will get dt is equal to, just check this out, what will dt be equal to? Take dt on the other side and take everything else on the right hand side. So it will be nothing but density will be there, latent heat will be there, thermal conductivity will go below, I believe. Thermal conductivity will go below, okay, along with 4 plus T, along with 4 plus T, obviously. And what else will be there? Think about it. Y will go on the top along with dy. Y will go on the top along with dy. Why did I do this? Because I know I can now integrate this. I can integrate this. So integrate this with this. What will be the limits? When you just start, the layer of the ice was nothing. So 0. Initially, there was no ice formed. So 0 ice at 0 time. When time t passes by, the layer of the ice is, let's say, y. Layer of the ice is y. So when you integrate this, this will just become t minus 0 is equal to rho L divided by k into 4 plus t into y square minus 0 square divided by 2. So therefore, the time taken will be rho L y square whole thing divided by k into 4 plus t. This is what I get. This is what I get. So this derivation, this formula is very, very important. Okay, y square by 2. I think I had to put 2 also over here. Yes. Yeah. this derivation, this formula is very, very important, which talks about the growth of ice over lakes. There was a question which was asked in NEET 2019. You can see the same question is there exactly, right? So you can solve it and mark the answer later on as option A, right? So this was asked in 2019. Great, ice formation over lakes. Same derivation, same formula, values were given. Hello, Alan. Shall we now go to Shall we now go to radiation, my dear warriors? Everybody ready for radiation? So that's what was there in conduction. It's time for radiation. Cool? Let's go. Full Josh. Yes, have you smashed the like button already? If you have not done that, please do it. Please do it. And I'm seeing that some students are chilling out right now. They are like, array, heat transfer, not important. Let me do ray optics. Ray optics already done. Or even rotational mechanics already done. So if you have not yet watched those classes, please watch it. Yes, I'm not stopping you, but does not mean you ignore other topics. If you start ignoring other topics, then you will suffer a lot later on. You will suffer a lot later on. Keep this in mind. So make sure you are covering up each and every chapter, my dear students, because every chapter is going to fetch you some marks, and those will only add up to give you 160, 170, 180 marks in your NEET physics, right? Let's go. Like I said, radiation, the fastest way of transfer of energy, and not just that. One second. So when I say radiation, radiation, it is obviously the fastest mode of heat transfer, mode of heat transfer. Where does it occur? Does it occur in solids, liquids, or gases? Well, there is no need of medium. No need only of medium. It can occur in anything. It doesn't matter. No need of medium for radiation to occur. Not just that, you can also say because it is radiation, it is actually in the form of electromagnetic waves. It is electromagnetic waves at the end of the day. So that's how these heat transfer occurs. Now, there is one fundamental difference between radiation and conduction. I believe NEET will ask a question on this someday. Maybe this year, maybe some other year, or maybe, year after that. And what is that fundamental difference is with regards to how radiation still occurs even when there is thermal equilibrium. This is very, very important with regards to radiation. And I'll come to that in a bit. First of all, remember that radiation occurs for every object which is having any temperature above 0 Kelvin. 0 Kelvin is the smallest temperature, that is minus 273 degrees Celsius. So even if an object is there at minus 270 degrees Celsius, minus 100 degrees Celsius, 0 degrees Celsius, 5 degrees Celsius, everything will emit radiation. And this radiation happens because of the collisions of the atoms, movement of the electrons, and electric fields and magnetic fields involved. And you will see electromagnetic waves are being created from the body, which has motion of the particles, motion of the charges. And this is a completely surface phenomena. That is why the radiation which is going to come out will depend on the surface area. More the surface, more the radiation. Temperature of the surface, and also the nature of the surface. You paint that surface some color, it will behave differently. You paint the surface some other color, it will behave or emit energy of different amount. Yeah. So we will basically now comment about radiation a lot. Let me come over here. Yes. Radiation, right? Any body above 0 Kelvin emits radiation, emits radiation. And it depends on, and it depends on surface area, surface area, temperature of the surface, temperature of the surface, and lastly, the nature of the surface. Nature of the surface. Nature of the surface. Very, very important. And this amount of energy which is going to be radiated, this amount of energy which is going to be radiated, I will write it as dq by dt, dq by dt, which is emitted or radiated. I can also write it symbolically as q dot. What is the dot symbolizing? What is that dot symbolizing? That dot is symbolizing derivative, rate of. So when I put single dot, it is derivative. If I put double dot, it will be double derivative. If I put triple dots, then it is triple derivative. That's all. That is the meaning of the dot. So because it is emitting the radiation, I will put a subscript below saying emit. Okay. Now this is rate of heat emitted. So obviously this is also going to be having the same units of joules per second or even watts. One and the same thing. One and the same thing. Okay, one and the same thing. This heat which is going to come out, this heat which is going to come out of any body, this heat which is going to come out of any body, because it has some temperature, this heat has a formula given by Stefan Boltzmann law. So there is a Stefan Boltzmann law which tells you how much energy will come out of it. And let me tell you, if you take any body like this, okay, take any body like this, according to Stefan Boltzmann law, this amount of heat which is going to be emitted, the heat which is going to be emitted from any body comes out as a constant E, constant sigma, area of the surface, temperature of the surface, whole raised to 4. This is a very, very important law. Let me tell you that. This is a very, very important of a very law for how much energy is being emitted per unit time. Senthil, you can try to do it on your own. If you still have doubt, you can do one thing. My Telegram channel is there, Captain Shreyas. Just put that doubt over there. I believe you should try it on your own. It is straightforward, just like what I've done. But still, if you have doubt, there is a group discussion. You can also comment on the Telegram group. It's called as Captain Shreyas, IDJ Neet, right? Just search it on Telegram, you will get it. We can discuss it. If you are not on Telegram, put up a comment with your doubt. I'll definitely get back to you. Cool? Is that fine, Senthil Nathan? Right. Now, what are these values? What are these numbers over here? This sigma is your Stefan Boltzmann constant, and it has the value 5.67 into 10 to the power minus 8 in SI units. It's very easy to remember this particular constant because look at the number 5, 6, 7, 8. They are arranged serially. 5, 6, 7, 8, one after the other. So 5.67 10 to the power minus 8 is a very easy way to remember. What is A? Is the area. Like I said over here, it depends on the surface area. It also depends on the temperature. Do you see? It depends on the area, just like we predicted it to be. It depends on the area, just like we predicted it to be. And also depends on the fourth power of the temperature. It depends on the fourth power of the temperature. The only thing which is remaining now is this one, which is the nature of the surface. Nature of the surface. The nature of the surface is decided by this value E, which is called as emissivity, emissivity of the surface, emissivity of the surface material, of the surface material. And this emissivity, remember, is 1 for a black body. For a perfectly black body, it is 1, and there is no such black body which you can make practically. You can reach close to it, but not exactly equal to 1. It's very difficult to reach exactly 1. So when I say emissivity for other bodies, usually, usually emissivity for other bodies is going to be 1. This means who will emit the most amount of energy for a given temperature and given area? Who will emit most energy for a given area and given temperature? That means, I tell you, this temperature is fixed, area is fixed, sigma to is a constant only. Who will have the largest energy which is being emitted? The one with largest T. What is the largest T possible? 1. For whom? Black body. Why? Because for other bodies, E is less than 1. Oh, so black body will emit the most. So black body, so for a black body, which basically emits the most. This is very, very important. This is very, very important. Is that absolutely clear in your head, my dear warriors? Also, this temperature has to be absolute temperature. Do not put, sir, the temperature I put it as 0 degrees Celsius. If you put 0 degrees Celsius here, you will get energy emitted is 0. Like, sir, no energy is emitted. One tight slap you will get. So don't put in Celsius, put it in Kelvin. Put it always in Kelvin. Keep this in mind. Is that okay? Oh, all right. Moving ahead, moving ahead, moving ahead. Yes. Now that we have talked about, Stephen-Boltzmann law and how every body emission is dependent on the area, temperature, and the nature of the surface, let's go to the next part of radiation. So imagine what happens is this radiation is falling, this particular radiation is incident on something else. So I will call this as the incident radiation. Incident radiation. And let's say this is the body on which the radiation is falling. Okay, this is the body on which this incident radiation is falling. There are one of these three things which can happen to the incident radiation. If something is falling on you, one thing is you can absorb it, right? You can directly basically absorb the radiation. So imagine if the incident amount of energy which is falling on you is Qi. Qi. So out of all that energy which is incident on you, you might absorb something at some rate. So I will call it as QABS or A, whichever you prefer it to be. So QA stands for the energy which is absorbed per unit time. So it is basically rate of energy being absorbed. So it is nothing but your rate of energy being absorbed. What is Qi? It is nothing but rate at which rate of energy incident. Rate of energy which is incident on it. If 100 joules is falling per second, out of that maybe 30 joules is absorbed. What will happen to the remaining? Maybe a part of it might just get reflected, So the part which gets reflected, I'll just put it over here. Some part has got absorbed over here inside. Okay, so the amount of energy which is reflected, I will just call it as QR with a dot. So this is rate of energy which is reflected. And there is one more thing which can happen. Neither did it get absorbed nor did it get reflected. It just went past through the body. So basically it got transmitted. It just got transmitted. So the last part of the energy might just be transmitted. So this is rate of energy, which is basically transmitted, So by energy conservation, whatever energy falls out of 100 joules, some part, let's say 30 joules gets absorbed. Let's say 40 joules gets reflected. So the remaining 40 plus 30 is 70. So remaining 30 might get transmitted. Is that right? Everybody with me? So we now define some coefficients. I'll show you what they are. So if you divide the entire thing with qi, you will get 1 on this side, 1 on this side, and over here you will have qa, then here you will have qr, and then qt. And since I divided the entire thing with qi, so I'll just put over here qi, qi, and qi. So the left hand side is 1. So this 1 will be equal to this ratio, which you see, how much energy is absorbed upon the total energy is called as the absorption coefficient or absorptivity. Absorption coefficient or absorptivity. Then the next term that you get is the reflection coefficient or reflectivity. And the last term that you get is transmission coefficient or transmittivity. So absorption coefficient plus reflection coefficient plus transmission coefficient, the total sum has to be 1, has to be number 1. Is that clear, my dear warriors? So what is A? A is basically how much is your absorptivity or absorption coefficient. Then what is your R? It is basically how much is the light which is getting reflected. Reflected. The last one is basically T, which is how much is getting transmitted. So it is transmittivity. This was reflectivity. Keep this in mind. Clear? Everybody till this point clear? Very nice. So say for example, I tell you, okay, actually before that we'll go to one more law and then we'll talk about that problem. There is this Kirchhoff's law here also, just like in current electricity. Kirchhoff's law of heat transfer and radiation. Imagine I talk about a black body. For a black body, what is so special about a black body? When something is black, that means it is emitting highest good, but it also absorbs everything. So for a black body, can I say absorption coefficient is 1? Right? For a transparent glass, for a transparent glass, what will the speciality be? Transmission coefficient will be 1, right? Transmission coefficient will be 1. So in case of transparent glass, transmission coefficient is 1. In case of black body, transmission coefficient is 0. So this will be 0 for a transparent glass. A will be 0. Even R will be 0 for both the cases. But for a mirror, for a perfect reflector, for a perfect mirror, what is the speciality? It will not absorb anything, it will not transmit anything, but it will reflect everything. So reflectivity will be 1. Reflectivity will be 1. So everything has different A, different T, different R in nature. Sometimes A might be 0.3, T might be 0.7, R might be 0.65. So different values are possible. I have taken the extremities of all the things, whether it is 0 or it is 1. Interesting thing to note is for this particular black body. A is 1, and just some time back I told you black body emits the most, and E is also 1 for a black body. E is also 1 for a black body. So if I write the value of E over here, if I write the value of E over here, E will be 1. Believe me, even for a transparent glass, the emissivity will be 0, and for a mirror, emissivity will be 0. Perfect, ideal mirror. Okay, which is not possible in reality, but this is a ideal situation. You will see A and E values are always going to be the same. In fact, Kirchhoff proved it. We do not have the derivation and all that, but he proved it, and he said that A is always equal to E. A is always going to be equal to E. So this also means good absorbers like black body are also good what? Emitters. Good emitters. And vice versa. Bad absorbers are also bad emitters. So if somebody, some student, this is also true in real life, some student can absorb everything, he takes all the feedback properly, he'll also be a good emitter, meaning that he will also give very good knowledge to everyone. But a student who does not, or a person who does not absorb, you know, much, he does not take positive feedback. He's like, oh, what are you saying? I will not take your feedback. They will also not give you good advices. They will not be good emitters. They will be bad emitters. So A is always E. That is what Kirchhoff's law is saying. It is also true in real life, right? Very good. Now, moving ahead, imagine a question where, you might have something like this question where, you know, incident energy, incident energy is 50 watts and transmissivity is zero point 0.2 and emissivity is zero point 0.1. Question is find absorptivity, find the energy which is basically getting absorbed, energy which is getting transmitted, energy which is getting reflected. This is the question. Okay, let's try to solve this particular question. Let's try to solve this particular question. Since emissivity is zero point 0.1 from Kirchhoff's law, directly from Kirchhoff's law, A will be equal to E. Therefore, A will be also equal to zero point 0.1. The another rule which we have learned is A plus R plus T is equal to 1. Absorption coefficient is zero point 0.1. Reflection coefficient not given. Transmission coefficient zero point 0.2 is given to you. So this is equal to 1. So R will be 1 minus 0.1 minus 0.2 means 0.3. So it will become 0.7. That is what your reflection coefficient or reflectivity will be. Now we can find everything. Now we can find everything. So how much energy gets absorbed? How much energy gets absorbed? It will be nothing but absorption coefficient into multiplied by how much energy is incident. So absorption coefficient is basically zero point 0.1, energy which is incident is basically 50. So this will be nothing but 5 watts. This will be nothing but 5 watts. Is that clear? Same way, how much amount of energy will, let's say, basically get transmitted? So it will be transmission coefficient into how much energy is being incident, because T is how much energy is transmitted upon the incident energy. Direct formula from here, whatever over here, right? This is basically transmittivity. So QT will be T multiplied by QI. That's all I have done, right? That's all I have. So how much will that be? How much will that be? Transmission coefficient is nothing but zero point 0.2 multiplied by 50. So that's going to make it 10 watts. Last one is reflected energy. In fact, you know the total energy, so just subtract the energies, guys. So total energy is 50, subtract 5 and also subtract 10. So you'll be left with 35 watts. As simple as that. So answer is 35 watts for this. Is that absolutely clear how we solve this particular question? These kind of questions are again common. Another kind of question which can come. Imagine they give you, if if the temperature is doubled, if the temperature is doubled, then emitted energy, emitted energy by radiation is how many times? How many times? If that is the question, what will you do? Remember Stephen Boltzmann law? Q dot was E sigma A T raised to 4. So Q dot is proportional to T raised to 4. So if somebody decides to increase the temperature 2 times, so the power of temperature is 4, so it will actually become 2 raised to 4, which means it will become 2 raised to 4 is how much? 4 square, which is nothing but 16 times. So the answer is heat emitted, heat emitted, heat emitted will become, how many times? Will become 16 times. That is the funny part. That is the non-intuitive part. It is not 64, it is not 32, it is not 8, it is not 2, it is not 4, it is 16 times. Is that clear? So this kind of question can also come in your NEET examination. Moving ahead, moving ahead. I was telling you that radiation is slightly different from conduction, and I told you that I will be telling it to you shortly. And this can be asked maybe sometime. You know what is different in radiation, which is different in conduction? This is what it is. Imagine if there is one body here and another body over here, and they are joined by some rod or something, and you are talking about conduction. So let me do one thing. Okay, observe this. Imagine this body is at 70 degrees Celsius. This is at 20 degrees Celsius. Same thing. This is at 70 degrees Celsius. This is at 20 degrees Celsius. This is at, let's say, 40 degrees Celsius. This is also 40 degrees Celsius. And this is also 40 degrees Celsius. This is also 40 degrees Celsius. On the left hand side, let's say we are talking about conduction. And on right hand side, let's say we are talking about radiation. Now see what is different in both of them. Very, very important. Okay. Observe this carefully. Observe this carefully. When you talk about conduction, 70 degrees Celsius, 20 degrees Celsius, hot, cold, heat always goes from hot to cold. You will see that the heat will flow like this. The heat is basically going to flow from the hot side to the cold side like this. This is the direction of heat flow. Heat will flow from the hot side to the cold side. And when thermal equilibrium is achieved, then you will see that there is no heat flow only. There is no heat which is flowing. This is at basically thermal equilibrium. This is at thermal equilibrium. This is what happens in conduction. But in radiation, this is not what happens. What you will see is even at temperature difference, heat will be flowing not just in one direction but in both the directions. In fact, there will be more heat which will be flowing from this side to this side. In fact, you don't even need the rod. Just a second. Because this is radiation, you don't need any medium as such. You will be seeing that there will be more heat which will be going this side. There will be more heat which will be going this side than the amount of heat which will be coming this side. But the point is the net heat will be going from hot side to the cold side. Heat will be flowing both ways. Heat will be flowing both ways in radiation, but the net heat will be flowing from hot side to the cold side. In radiation, in conduction, sorry, heat was only going from hot side to cold side. It was not coming from cold to hot. You can see in radiation, heat is also coming from cold to the hot, but it is in smaller amounts. So maximum is going from hot to cold. So the net flow is from hot to cold. Is that clear? So now you can guess what will happen at thermal equilibrium. You will see if there is some amount of heat which is flowing from this side to this side, you will also see the exact same amount of heat flowing from this side to this side. So heat flows like dynamic equilibrium, but net heat, net heat flow is basically a big fat zero. Net heat flow is zero. This is the most different thing which is there in radiation. Not many people know that. You ask many students, they will not be able to tell you this. And you might have a question on this. And this is also called as Prevost theory of heating. Prevost theory of an object getting heated. Okay, so let me put that over here. Prevost theory. Prevost theory. If you have an object and you see that these are the following cases which can happen on it. First case, it is absorbing more. It is absorbing more heat than the amount of heat which it is emitting out. Than the amount of heat which it is emitting out. Second case, it is emitting out more heat. It is emitting out more heat than the amount of heat which it is absorbing. And the last one, it is absorbing same amount of heat as the amount of heat which it is emitting out. These are the only three possibilities. In the first case, just one second, let me just duplicate this. In the first case, when you see that the amount of heat absorbed is more than the amount of heat which is emitted, what will you see? Absorbing more, releasing less. So it will get hot. So it will get hotter. It will get hotter. It will basically get hotter. That means the temperature increases. The temperature increases. When absorbed is less, emitted is more. Absorbed is less, emitted is more. Then you will see that the temperature decreases. The temperature will decrease. And in the last case, when amount of heat which is absorbed is equal to the amount of heat which it is emitting out, then what will you see? You will see that it will be in thermal equilibrium. It will be in thermal equilibrium. Thermal equilibrium. So, I would say that the temperature is going to be constant. Temperature is going to be constant. Yes. So in fact, this gives us the final formula. This gives us the final formula of, what might be the net heat flow rate which is happening, because now you can see from previous theory that Q net will be nothing but how much heat is being absorbed minus how much heat is being emitted. How much heat is being emitted. So the difference of this is the net heat flow which is happening inside the body. Is the net heat flow which is happening inside the body. This is what Prevost theory is telling me. And this is what leads us to the final modified formula of Stephen Boltzmann law. Remember, just some time back, I told you what QE is. QE was nothing but E sigma A, temperature of the body raised to 4. This was Stephen Boltzmann law. The same Stephen Boltzmann law is also there for absorption, just that instead of emissivity coefficient, you have absorptivity coefficient. You have the same sigma A, but because it is absorbed, where will you absorb it from the surrounding temperature. All the energy from the surrounding is being absorbed in the body. So here the temperature is of the surrounding, so surrounding raised to 4. But wait a minute, I know by Kirchhoff's law A is also equal to E, so it will become E sigma A Ts raised to 4. Ts raised to 4 minus E sigma A T raised to 4. Now you can see many terms are common in both of them. Just like E is common, sigma is common, even A is common. So the only difference will come of basically your body temperature and the surrounding temperature. That's all. So this is your net heat flow rate. This is your net heat flow rate. Is that absolutely clear? So what is TS and T? I'll mention it over here again. This is the surrounding temperature. What is this? This is the surrounding temperature, and this is the temperature of the body. Temperature of the body, which we are talking about. This is the net heat flow rate. Very, very important formula which we got from Prevost's theory. Correct? All these pointers are important, and I've given beautiful, beautiful handwritten notes for all of you. I think this will be very useful for you to revise. I hope you are loving the notes that I'm giving. These are all proper handwritten notes. It's nicely colored for you to understand all these things. Okay? Now there is one last thing which is there in radiation. We'll just have a look at it before going to the final set of questions coming up on your screen. Wien observed a very interesting thing, and he saw that if you have any body which is at some temperature, okay, this is a any body at any temperature, it emits radiation of different amounts, but this radiation is not of same wavelength or same electromagnetic frequency. It is of different frequencies. Sometimes the frequencies are very less, sometimes or the frequencies are very more, so the wavelength is more or the wavelength is less, like that. So you have different wavelengths coming out of a body. So I would say the radiation emitted from a body has different lambda, or basically frequency, have different wavelength or frequencies, but there is a particular frequency or wavelength which is emitted the most. Particular wavelength or frequency which is emitted the most. So maybe this particular wavelength you will see the most everywhere, everywhere. Which is that? It depends. What does it depend on? We'll come to it. But very few wavelengths of very small frequency or of very large frequency, or very small wavelength or very large wavelength. Most of the wavelengths are of a particular type. A certain, I would say, lambda, I will call it as lambda max, has highest proportion, has highest intensity among the all, among all. That is called as lambda max. And this lambda max is found out, lambda max is found out to be inversely proportional to the temperature, is inversely proportional to the temperature. In fact, the law becomes something like this. The law becomes something like this. It becomes lambda max multiplied by T is roughly around 2.98 into 10 to the power minus 3, which is called as the Wien's displacement law, which is called as the Wien's displacement law. Right? This lambda max is inversely going to be proportional to the temperature, and this formula, which is lambda max into T, is 2.98 into 10 to the power minus 3, tells you that it is inversely proportional, like you can see over here. This is called as the Wien's displacement law. So how does it look like to draw this Wien's displacement law on the graph? And that is what you should know. So you draw wavelength on the x-axis and not temperature. Don't draw temperature. You show the amount, basically the intensity of that radiation of that particular wavelength. Intensity of that particular wavelength. Usually, you will see that the radiation intensity will look like this. Oops. Wow. This is how it will look like. I hope you are able to see that there is a lambda max over here. Certain wavelength is of maximum intensity, maximum amount, maximum proportion. So that is the color which will come out of it in maximum proportion. If you heat it, temperature increases, lambda max decreases. So when you make the body cold, when you make the body cold, the graph goes like this. The graph goes like this. So this is a colder body. This green one was for a hotter body. What you can see is a noticeable shift in the lambda max. You can see the lambda max has shifted towards your left hand side. That is why it has been set to displace. And that is why this law is called as the Wien's displacement law. The lambda max shifts. So when you heat something, the maximum color which comes out, the wavelength will reduce. In fact, this is the exact law which is used to detect the body temperature at airports, especially during COVID. You might have seen they use a scanner and somehow they are able to detect the temperature without putting a thermometer under your arm. How? That sensor measures the wavelength which comes out of your body. You are also a body, you will emit wavelengths. At 37 or basically 96, 97 Fahrenheit, certain wavelength will be maximum, it will be present in maximum amount. If you are having fever, your temperature will go from 96, 97 to 100. So what will happen? The wavelength will change. If the wavelength changes, the detector, the scanner will detect it. This person has fever. So Wien's displacement law is used in your thermal scanners, and especially you might have seen the usage of it in COVID. Understood the application of Wien's displacement law? Everybody with me? Clear? Right? So let's see some questions. The fastest mode of heat transfer. Let's do some quick questions before going ahead. Yes, conduction slow, convection little bit fast, radiation really fast, speed of light. It's not going to be equal for all. So answer is radiation. Correct. Very good. Yes, on decreasing temperature, lambda max will increase. Yes, Mohana Sujay. Last one. We consider the radiation emitted by human body. Which of the following statement is true? Radiation emitted is in infrared. Radiation is only during the day. Radiation is only during summer. Radiation lies in ultraviolet and hence not visible. So you might have heard, sir, I saw one thermal scanner goggle, sir. You can see the person even in dark, even when there is no light. These are thermal goggles or thermal vision. What do they depend on? They depend on infrared detection because your body right now at 96, 97, 98 Fahrenheit, the wavelengths which are coming out are in the infrared region. In fact, you might have heard of certain reptiles which can see humans even in the dark, like snakes. How? Because they can detect infrared region. They have infrared vision, and God has naturally gifted these animals. You cannot see it, but you are right now emitting infrared region. So humans at normal body temperature emit infrared radiation. Got it? So keep these things in mind. This was asked in AIPMT 2003. So these were some of the interesting facts about and the concepts of your radiation. You will see that we have done most of the questions. More question practice, we'll be doing it in the days to come in the form of PYQ and revision classes. But for now, at least I hope you have got that confidence in radiation, you have got that understanding in radiation, and you have got that enough practice in conduction, which is most likely going to be the case in or asked in the Neet 2024 or 2025 examination. And if you want more practice, more assignments, more DPPs, make sure you enroll yourself in the crash course, because the crash course is just for 1999. If it was high price, I would not have you know been telling you about it, but the price is so good. I feel that you should definitely make use of at least the material. Okay, at least make use of the content which is given over there. Make the best use of it, right? Cool. And yeah, if you want to enroll in the offline batches, the option is there. The links are there in the description box. So Neet 2024 crash course link is also there in the description box below. I hope you guys had a great session. Yes, heat is done and corona temperature checking. Yes, Jai Ganesh. Bye bye. Take care. So heat thermal physics done completely. It's now time to move on to anything which is small and remaining. We'll complete that as well. Okay. Bye bye. Hasta la vista, Captain Shreyas signing off. Take care.